Let's take a look at this task number 19 about filtering. We have a power line filter, and this should be a low pass filter. So we might have some power electronics, right, that create high frequency disturbances, and still our low frequency, our energy sickness should get through this low pass filter, but the high frequency disturbances by this, what is mentioned here is a thyristor control unit, they should be filtered away. And then there are some requirements, and this would be something, let's say, that we have in practice. So the cutoff frequency, the corner frequency should be 200 Hertz. So let's say 50 Hertz components gets through, maybe also 150 Hertz third harmonic, but all higher frequencies should be attenuated. And at 10 kilohertz, which might be the switching frequency of this thyristor control unit, we should have some attenuation, of 60 dB. And then the source impedance is 1 ohm. It's quite small as usual for energy systems, because there you don't want to have high source resistance because it would lower the efficiency. And the load impedance is rather high because it might be, let's say, something ohmic inductive. And so then at high frequencies we might have some higher impedance there, but at the end it's just a value and we need to assume something. But let's say this is rather high. The DC gain should be 1, and it, as mentioned before, it should be a Butterworth filter. And so now the first question that we need to solve is, what order should this filter have? And then the order also tells us how many reactive elements do we need in this filter. And so, for this task A, what ideas do you have to calculate what should be the order of the filter?
First, every decade of the common frequency.
Exactly. So we can say if we have a first order filter, then we have 20 dB per frequency decade of filtering. Or of attenuation, let's say. If we have a second order filter, it will be 40 dB per decade. So we can check that our corner frequency is 200 Hertz. So one frequency decade, if we multiply the frequency by a factor of 10, then 10 times this cutoff frequency or corner frequency would be 2 kilohertz. And if we multiply it by 100, if we have 2 decades, if we have 100 times this corner frequency, then we will have a frequency of 20 kilohertz. And so if we have a first order filter, this would mean at this 2 kilohertz frequency, we would have 20 dB of attenuation. If we have 2 frequency decades, this would mean we have 40 dB of attenuation. But at 10 kilohertz, we already want to have 60. So first order filter is probably not sufficient. So then if we check for the second order filter, for 1 frequency decade, we would have 40 dB. For 2 frequency decades, we would have 80 dB. And okay, this 60 dB at 10 kilohertz is somewhere in between. But probably this second order filter would be sufficient in this case. I would say we could just use this as a lucky guess at this time. Of course, we can also, or do you have any other ideas how to determine the order of the filter that we need in this case? Or you can check the lecture slides. And for a Butterworth low-pass filter, there is this formula given for the amplitude frequency response. And so within this formula, we have some normalized frequency that is called your omega. So that is not ohm, that is the frequency divided by the corner frequency. We have some DC voltage gain, and we have this filter order. So we could, of course, also use this formula. So I will copy this and paste it here. And so now, if we would like to get the filter order, we would need to rearrange this equation to the direction of n. So yeah, how can we get n from this equation? Any ideas for this? Yeah, we have to remove the square root, and we have this n here in some exponent, in some power. So, and it's in the denominator of some fraction. So it's usually a good idea to, let's say, bring this out of the denominator. So we can, and maybe square this equation, right? Okay, so then we have 1 plus omega to the power of 2n. And on the other side, we have a of omega squared divided by a0 squared. If we bring this to the no, exactly the other way around. So yeah, if we bring this to the top, we need to divide by this. So it will be a0 squared divided by a of omega squared. Okay. And so then we need to get rid of this 1. So we say, okay, minus 1. And then we need to get this exponent. So how do we get this exponent? Yeah, with some logarithm function. Yeah, because if I don't know, a to b equals x, then the logarithm of x to this base a equals b, right? So yeah, this should be correct. And so now we want to have this b there. So it's the logarithm of this x to the base of a. And in our case, this base is omega. So 2n should be the logarithm to the base of omega of a0 squared divided by a of omega squared minus 1. And then the remaining question is, how can we calculate this logarithm? How can you calculate some logarithm of x to base a using other logarithms? You have an idea? Okay, so I think it should be something like we take, for example, log 10 of x divided by log 10 of a. And so we can do the same thing here. And the remaining thing, as usual, I will do an octave. So there is my octave window, which should open up. And of course, then finally we need to divide by 2, right? So I could also write here to get rid of this 2. There we take 1/2 of this. Okay, so let's check in our octave window. And let's insert all these values that we need. So A0, the DC gain, as mentioned in the task sheet, should be 1. Then we have a cutoff frequency, a corner frequency, FC of 200 Hertz. And the frequency that we are interested in is 1 kilohertz. So 10 kilohertz. And kilo is 10 to the power of 3. And so from these values, if we check the lecture slides, from frequency and cutoff frequency, we can calculate this omega, this normalized frequency as it's called. So omega is frequency divided by cutoff frequency or corner frequency, and we get some factor of 50. And so now A0, okay, and of course we need to have this A, and this A should be 60 dB. So A in dB is 60. How can we convert this 60 dB in some attenuation? So this A of omega in linear units, 10 to the power of this A in dB, and then divided by 20 because it's proportional to a root power quantity to some current or voltage or something like this. Okay, so A dB is 60, this A of omega, or A depending on omega, is 10 to the power of A in dB divided by 20. And so then we get a factor of 1000. This is something that we could have also calculated in our head, but okay. And so A0 divided by A0 squared divided by A of omega squared. Right, this is what I have here in this formula. So then this minus 1, this does not make too much sense because we get something negative. I think, let's quickly check the task once again. This should have some attenuation, and the formula that we have here is the amplitude response. It's not really the attenuation. It's 1 over the attenuation. Yeah, the attenuation, this is like transfer function. Here, this is getting smaller with going to higher frequencies. And what is given in our exercise task is the attenuation. So we need to have minus 60 dB of transfer. So let's go back and say the A dB is minus 60. And so this A of omega is then 1 over 1000, something smaller. So if we go back to our A0 squared formula, now we have 1000 divided by 1 is 1000 squared is 1,000,000, and 1,000,000 minus 1 is 999,900. Okay, so now from this, we need to take this logarithm to the base of omega, and then half of this, and this should give our filter order. So we take, I don't know, any log of this. So the log of this divided by the logarithm of omega. And I need to have more space here for typing. So this divided by omega, and now this divided by 2, or 1 over 2 multiplied with this. So this is our formula here, and this is n. This is the filter order. And so the n that we get from this is 1.7 Do you remember the value? No,
1.77.
1.77. Okay, 1.77. And so, of course, then from this, what do we say? It should be 2. It should be the next integer number. So the seal of this. So n, we need n of 2. So in Octave, we could say we always need to round this to the next integer number. And then we get this 2. Okay, with this, I think we have successfully finished task A of this task. Which questions do you have related to this? No questions, okay. So then we can continue with task B, and I will take a different color. And yeah, so the question here is, what would be a meaningful filter construction structure, and why do we choose this arrangement of the filter elements? So we have a second order filter. Maybe let's draw the source first. So we have some source, and the source has some inner impedance that is given there, the ZS, this 1 ohm. And here's our source voltage, US. And so here's where our filter starts. Let's say here's where our filter ends. And attached to this, we have the load impedance ZL. And now the question is, well, it's not complex. But this is 1 kilo ohm. So, yeah, the question is, what filter elements do we choose and in which arrangement? Any ideas? And it should be a second order filter. So second order filter means how many filter elements do we need? 2. And so, so what would be good is to have some inductor and some capacitor, and it should be a low pass filter at the end. So where do we need to place the inductor? Or in which arrangement should we place the inductor? I mean, we have the choice to put it as a series element or as a shunt element. As a series element. So we need to have some inductor in series. Let's draw some inductor. Because the impedance of this inductor ZL is not to be confused with the other L here. So this is the complex ZL is J omega L, and the higher the angular frequency, the higher will be impedance. So low frequencies can get through, but high frequency components will be blocked. Okay, and so then the question is, where do we place the capacitor? To the ground, like a shunt element, but do we place the capacitor rather here or rather there?
Oh, previous to that.
Before the inductor or behind the inductor? Before. Okay, let's draw some capacitor here, and let's think about this. So the impedance of the capacitor ZZ is 1 over J omega C. So the higher the angular frequency, the smaller the impedance, and so high frequency components will be dissipated to ground. And I think, I mean, maybe we can try it later on, but I would say this arrangement will not work that well because we have a rather low impedance here. And so we also have a low impedance here, low impedance and low impedance. Okay, but it's not super efficient. I think it is better for the high frequency rejection. Low impedance here. We have then in comparison a rather high impedance here. And whatever gets through would need to go into this high impedance load, but it could also go over the low impedance capacitor. So from my point of view, it would be it would be more feasible, and we can, as said, we can try it out later on. What will happen if we place the capacitor in front, but I would rather place the capacitor here at this position. So this is our filter arrangement. And this would be the reasoning why we choose this arrangement of these filter elements. Then let's continue with task C. Calculate the necessary values of these filter elements and what will be the problem if the filter has to be built or would have to be built in reality. So I will try to copy this schematic here and paste it to the next page. And maybe we can go back to the previous page and quickly check once again, it should be a Butterworth filter. And it should be a Butterworth filter of second order. So we can check our lecture slides material. And there's this amplitude frequency response given. And here we have the corresponding polynomials for different orders. And so the second order polynomial should be this one here. Maybe I can also copy this. And Francesco, maybe you can close the door.
Sure.
And so paste it somewhere here. And then this should be the polynomial in our function, in our amplitude frequency response function, and the magnitude of this amplitude frequency response should be this. And I think because this is complex here, it's really this function. So we can check there's some A0 in front or some A0 at the top in the numerator of this fraction. So at the end, we should end up with something like this for our filter. That's the goal. So, but how do we get there? And so this transfer function, this amplitude frequency response, is also the ratio between the output voltage and the input voltage, and both are complex phasors. And the output voltage would be this voltage here at this position. The input voltage would be the voltage here at this position at the input of our filter. So yeah, once again, how can we derive this transfer function? We once again use a voltage divider. This always worked. So let's take some voltage divider once again and say the output voltage, which is the partial voltage divided by the input voltage, which is the total voltage, is partial impedance, and this is ZZ, the complex ZZ parallel to our load impedance, and the total impedance is the same thing, ZZ parallel to the load impedance ZL, and then plus, to don't add confusion here, I will write plus J omega L, plus this impedance of the inductor here. Okay, so yeah, then I would suggest to simplify maybe this expression a little bit. So ZZ parallel to ZL is how to calculate the parallel circuit of two impedances. Yeah, 1 over J omega C. Okay, we can try to do it this way. So 1 over the impedance, and in this case it's J omega C, and then plus 1 over ZL. Does not look too bad. Maybe we could get rid of this double fraction by expanding with ZL. So then we get ZL divided by 1 plus J omega C and ZL. Okay, and so this is what we can use and insert here and there inside our voltage divider. So then we get ZL divided by 1 plus J omega C and ZL, and in the denominator we also get the same expression, ZL divided by 1 plus J omega C ZL, and then plus J omega L. Okay, now we want to get this to be similar to this one here, more or less. And we know A0 is similar to 1 or is equal to 1. So we definitely need to have some 1 in the numerator of this fraction. And so what do you suggest to do to get a 1 in the numerator? Divide by ZL. So if we divide by ZL, it disappears here, there, and we need to divide by ZL here. And multiply with this other denominator, multiply with this one. So this one will disappear here, it will disappear here, but here we need to multiply with this one. So 1 plus J omega, you know what I mean. No, this is not looking nice. 1 omega, The drawing pad does not work nice at the towards the corner. Okay, so then if we just copy this, so in the numerator we now have a 1, and here what is left is also a 1, and then we have 1 plus J omega L divided by ZL multiplied with 1 plus J omega C ZL. Okay. Not quite yet there, but it's not looking too bad. Yeah, because we have a 1 here, we have a 1 there, we have a 1 here, we have a 1 there, and we have plus something. So next step is probably to just calculate what is written there. So we have 1 divided by 1 plus, and then we have some term with J, and inside this J term we have omega L, and we divide by ZL. Right, that's all what we get here. And then we have this minus omega squared term, and J times J is minus 1. So we get the minus already. We get omega squared. And yeah, we get all the remaining stuff. So we get L and Z and C, and the ZL will cancel each other. So we get omega squared LC. Oh, nice. Not too bad. Not too bad. Okay, so now we can check. This here should be omega, or no, this here should be omega squared. So we can, all right, we can, let's take a different color. Say this here is omega squared. This should be also omega squared. So omega squared is frequency divided by corner frequency, or omega divided by cutoff angular frequency, and of course squared. And this is the same as, maybe let's continue here. This is the same as omega squared L times C. So from this we can say, okay, our corner frequency should be what is the corner frequency that we get from this equation? Yeah, so now this here should be the same as 1 over this, right? So the corner frequency should be 1 over square root of LC. And this also makes sense because if we do a quick check with the units, the unit of the unit of the inductance it's volt seconds divided by ampere. This is Henry. And the unit of the capacitance is ampere second per volt. This is farad. And so the amperes will cancel each other, the volts will cancel each other. We get seconds squared, and the square root of this is 1 over second. So this nicely makes sense. Okay. So we know our corner frequency should be 1 over LC, 1 over square root of LC. Okay, and so this is what we then can insert here into this term. So let me take another color for this term here. And so now this, maybe without the J, square root of 2 multiplied with omega should be the same as this one here. So square root of 2 times omega should be the same as omega L divided by ZL. And omega, as we have discussed, is omega divided by omega C. And omega C, we have already calculated, is 1 over square root of L times C. So we have another square root of L times C here. So if, and then of course, I can cancel omega on both sides, and then it's probably not a bad idea to rewrite this once again. So we get square root of 2 multiplied with square root of LC. And on the other side, we get L divided by ZL. And so now we have 2 equations for 2 unknowns. We have one equation. We know the corner frequency. The corner frequency is 200 Hertz. So we can calculate this angular corner frequency or cutoff frequency. And we know ZL. And so we have 2 equations for 2 unknowns, L and Z, or L and C. So now we need to solve this system of 2 equations. Yeah, any ideas for this? So what I would probably do is I would rewrite here on this side this, for example, as L square root of L squared. And so then we could also rewrite this as the L as square root of L times square root of L. And so then we could cancel one square root of L. And we could maybe, I don't know, rearrange this equation into the direction of Z and insert it here, or insert this equation into the direction of L or C and insert it here, something like this. So I would, for example, rearrange this equation in a way that square root of C is equal to 1 over omega C multiplied with square root of L. Is this right? Should be right. And so now we can take this equation and, for example, insert this into this C here, to eliminate the C, and then we just have some equation that depends just on L. Then we can calculate the L, and once we have the L, we can calculate the C. Okay, so then the blue equation will give us square root of 2. Here was just square root of C. Instead of this, I write the green term, 1 over omega C square root of L. And on the other side, we still have square root of L divided by ZL. And so now we can bring this to this side. So here the square root will cancel, bring the ZL to the other side. So then we have here ZL. And then we have some equation that L should be square root of 2 times ZL divided by omega C. And so this is what I will use now in my Octave window here back again. So our corner frequency we had, angular corner frequency is 2 times P times F. And ZL, I think we don't have yet. This is 1 kilo ohm according to our task sheet.
We have FC there in omega.
And we need to have in the omega C, we need to have FC, of course. Very good point. So then L is the square root of 2 times ZL divided by omega C. And we get some value of 1.1256, right? No, 54. And the unit, if we check the unit of ZL is ohm, and ohm is volt divided by ampere. And the unit of the angular corner frequency is 1 over second. So we get some second here. So we get volt seconds divided by ampere. And this nicely makes sense because this is the same as Henry. Okay, so we can then take this L and insert it here and calculate the C. And the C, if we want to have the C, then of course the C is 1 over omega C squared multiplied with L. And maybe then I have some space to write down the value there and to also check the units. So C is 1 over omega C squared and divided by L. And yeah, this is maybe not looking that nice. So I will multiply by 10 to the power of 6. Then we get microfarad, hopefully. So 0.5627 micro. And yeah, the unit of the inductance is volt second divided by ampere. And we have angular frequency here squared. So we get another second squared there. And then seconds and seconds will cancel each other. Or second square will cancel each other. We get ampere second divided by volt. And this is farad. So we get 0.562 something microfarad. And we have successfully determined the values of these filter elements. And so now we can maybe quickly discuss what would be the problem if we build this filter in reality with these values. It's a super big inductor, and it's also a quite big capacitor. Yeah, so remember the values that we had in the experiment. There we had something like 0.22 microfarad, and this was already a quite huge capacitor. And usual inductors have some millihenry, maybe some tens or hundreds of millihenries. But if you want to have more than a henry, you need to really have a very big coil, lots of wire, And yeah, if this wire should also need to carry a high current, then you need really, really big inductors, really big coils. And if this capacitor needs to withstand a rather high voltage, then it will be also a very heavy, big and bulky and expensive capacitor. And that's exactly the problem with this filter. So yeah, power filters that with small cutoff frequencies means you always need to have big inductors, big capacitors. And this makes it big, heavy, expensive, and so on. So what would be a solution for this in practice? How could we possibly improve this? Yeah, we could, like a digital filter, some active filter, something like this. So we could use other power electronics that are maybe more advanced than this, somehow measure the disturbance current and try to insert the disturbance current or couple the disturbance, the opposite of the disturbance voltage into our system. Do something like these noise cancelling headphones do, but just with current and voltage in our power system. And this will hopefully then get rid of the low frequency disturbances of our thyristor control, for example, or of the motor control unit. But the price that you need to pay is, of course, you create the power electronics, then will create disturbances at higher frequencies. But for these higher frequency components, okay, then we can use a linear filter or we can use this passive filter. But if the cutoff frequency is then not 200 Hertz, but let's say 20 kilohertz, something like this, then L and C must be much smaller. So no problem with this. Okay, so then what I would suggest to do is to plot this function in Octave and to check how it looks like. And then we can maybe also try this different alternative and move the capacitor here to this side and try to check once again what happens there and how this function looks like. So I will go back to my Octave window and try to calculate this stuff here. So we have Z. Yeah, and so for this, we need to have, of course, a frequency range to plot it. So let's use a logarithmically spaced frequency range, and let's start with something that is smaller than our corner frequency. So maybe 20 Hertz, and maybe go up to 20 kilohertz. So 20 E3. And maybe use 1,000 points. This should be sufficient. So there's our frequency space. And as usual, I forgot the second log 10 here. So then we need to convert this into angular frequency. So it's 2 times P times F. Okay, and I should have maybe escaped this. And so then we can calculate ZZ, which will be 1 divided by J times omega times C, and we also get lots of values for this. ZL we already have, and the ZL of the inductor is J times omega times L. Okay, and so then we can write down our transfer function there, output voltage to input voltage. And okay, before we do this, it would be good to have some function that does us a parallel connection. So parallel circuit of 2 impedances is, so we could use the same formula as over here, or we could also use this. It's the product of the 2 divided by the sum, right? Okay. So, and now we can write down our transfer function, and this is written on top there. So it's the parallel circuit of ZZ and ZC and ZL, the load impedance. And then we divide this by, once again, the parallel circuit of ZC. And I need more space or a smaller font. ZC and ZL, the load impedance, and this plus ZL of the inductor. And hopefully this should be it. So yeah, no errors, no complaints. And now we can plot this, and as usual I will use a logarithmic scale, and as a function of frequency we will take a look at the magnitude of this. So what is the magnitude transfer function? And the result that we get looks like this. Maybe a grid would be helpful. So now if we check, here is 10 Hertz, here is 20 Hertz, here our function starts. Here is 200 Hertz, here's 100 Hertz, here's 200 Hertz, here's our corner frequency. Here was the 10 kilohertz, here was the frequency of interest. And so if we convert into dB, so if I change to some semi-log x, and if we take 20 times log 10 of this, then we should convert it into dB. So let's also switch the grid on once again. And so and we can see, okay, our DC gain as before, 0 dB or a factor of 1, and at 10 kilohertz we really get more than the 60 dB. And so this is how this filter function of, or the transfer function of our filter looks like. The attenuation would be just the inverse of this. And yeah, so this is also how this function of a Butterworth filter looks like. The Butterworth filter is, let's say, very flat here, and yeah, also has a certain already quite a high attenuation at this corner frequency. If we take a look at the phase response in a second plot and take a look here at semi-log x and the angle of this, and this will be in degree, in radians. So if we want to have it in degree, we multiply with 180 divided by p. What would we expect? Before I plot, we have a second order filter. We should start, of course, with 0 degree phase shift, and then we should go to minus 180. And so if we do this and plot this, then it looks like this, and it's also looking meaningful and nice. So this is amplitude response. This is phase response of our second order low pass Butterworth filter. And this phase response is also rather smooth. This is one property of this Butterworth filters. What we can do then as the last step for this exercise task, we can maybe go back to this orange arrangement that we proposed at the beginning. And for this, of course, we need to write down our voltage divider here in a different way. And I don't know if I have some space here, maybe here. So if for this orange way, if we would write down our voltage transfer function, yeah, so no capacitor here anymore. So the only, yeah, so the only element that we have is ZL. And so then, yeah, it's a question, it does not really make sense if we take then this as the input voltage from my point of view, because then our voltage divider would be just ZL divided by j omega L plus ZL. So I would suggest to move the input voltage here to this position. And yeah, so the the total voltage, yeah, this is now really getting complicated. So this is gone. So yeah, good question what we do here. I think we need to have some step in between, right? We need to go from this voltage to this voltage here across the capacitor. But I would say it's not really our input voltage. So we need to have one voltage divider going from ZL, J omega L plus ZL. So from this voltage to this voltage here in between. And from this voltage, now we could go to our new input voltage. And so here now, then we get the equivalent impedance of all this. And this is ZZ parallel to J omega L plus ZL. And then we have the same term ZZ parallel to J omega L plus ZL plus our source impedance. And yeah, I think it's a little bit like comparing apples with oranges, because it's not the same reference, it's not the same input voltage, but let's see what we get in this case. So orange case means so I need to, no, I think this does not help me too much. Oh, this Octave prompt sometimes is not as convenient as in MATLAB. Okay, so ZL divided by ZL of the inductor plus ZL. This is the first fraction. And then multiplied with the parallel circuit of ZZ, and the parallel branch is ZL of the inductor plus ZL. I'm confused here if this was really typed, but I think so. No, here's some D is missing. Tab. The tab did not work. Okay, so, and this divided by the parallel circuit that we just had of ZZ and ZL of the inductor plus ZL, and this plus Z source. And the source impedance, I think I have not defined yet, so there will be some error message. So Z source is 1 ohm, and now this works. And so I can go back to figure 1, and in figure 1, do the semi-log X plot of the amplitude response. And this now looks like this. And if we add a grid, yeah, you can see it's not looking that nice, right? We only get something between 30 and 40 dB in this case. And so if we go to a second figure, and if we in the second figure do the phase plot, and maybe also add a grid for this, yeah, then you can see grid on. We also only get more or less to the 90, but it looks like that then there is a second corner frequency somewhere, and only starting from the second corner frequency we would get the real 40 dB per decade of attenuation. So to check this, if I go back to where I define my frequency range, and now if I, let's say, go to 200 kilohertz, or maybe even to 2 megahertz. So recalculate ZC and recalculate ZL and recalculate transfer function, go to figure 1, do the magnitude plot at a grid. So there we go. First corner frequency, second corner frequency. And figure 2 at the phase plot. And so we go to, we have the first cutoff, first corner frequency somewhere here. We transition to minus 90 degree, and then we have another transition, finally go to minus 180 degree. And maybe, and probably, if we, for this case, from this function here, would recalculate L and C, we might get different values that might behave a little better. But already looking at this function here, it's much more complicated than this one. So it would probably be much more complicated to do this comparison that we did here. And once again, from my point of view, it's still somehow comparing apples and oranges, because now we have a different voltage reference than before.